So in this video, I will prove the identities that I showed you in the previous video. Let's go ahead. So this rectangle here is what I want to prove, okay? That if A is unitary, then A dagger times A equals the identity matrix. And also the columns of A form an orthonormal set. So A is unitary means that A conserves the length of vectors, right? Yeah, that's equivalent. So that's the meaning that A is unitary. So we want to prove basically two things. The first thing is that if A conserves the length of vectors, then A dagger times A equals the identity matrix. And second, we want to prove that if A dagger times A equals the identity matrix, then the columns of A form an orthonormal set. So let's start with number one. So proof of one. If A conserves the lengths of vectors, what does this mean? It necessarily means that the length of a vector x is equal to the length of a vector A times x. Right? So when we apply the transformation A, the length of the resulting vector is not changed. Yeah. So remember, we have a vector x. We are applying the transformation A, and the output is A times x. So the lengths are the same. If the lengths are the same, we can say that the square of the lengths is the same. Yes. But if we write this using the inner product, this is inner product of x with x is equal to the inner product of A times x with A times x. Okay? So this is by definition of being unitary. Next step is we apply the notation of the Hermitian conjugate. So remember that we knew that the inner product in the physics convention can be written as A dagger matrix multiply times B. So we can do that here. This is what we do now. And what we get is that x dagger times x is equal to ax dagger times ax. Right? This is what we found earlier. Now we apply the properties of the dagger operation. In particular, remember that AB dagger is equal to B dagger times A dagger. Remember that we had to flip when we apply the dagger inside the parentheses. Yeah. So if we do that to the right hand side, we get that x dagger times x is equal to x dagger times A dagger. That's the left hand side, and then times A times x. Yeah. So we could have the parentheses like this. Or we know that we can use the associative property, so we can just remove the parentheses. The order in which we multiply things out doesn't matter. Yeah. And now if we compare the left-hand side with the right-hand side, it is obvious that this thing in the center must be equal to I, because the left-hand side has to be equal to the right-hand side. So this operation here in the center must be equivalent to doing nothing. And therefore, A dagger times A equals I, which is what we wanted to prove. So we have proved the first statement. Yes? Okay, what about the second statement? We want to prove that if A dagger times A equals I, then the columns of A form an orthonormal set. So in order to do that, I'm going to do a visual proof. We could do it the formal way with equations, but in this case, I'm going to do it visually. Okay? So I'm going to write A dagger times A I'm going to write it in terms of the columns of A. So let me clarify what I'm going to do. I'm going to write A as its different columns. So it has a column 1, column 2, all the way up to column M. Yeah, because A is a n times M matrix. Yes. And then this means that A dagger, we can write it in terms of their different rows. And we know that each row of A dagger will be the corresponding column of A, but complex conjugate. Therefore, the first row of A dagger will be C1 conjugate, this vector here, right? Because we have applied the Hermitian conjugate to matrix A. The second row will be C2 conjugate, all the way up to the mth row, which will be Cm conjugate. And this is a m times n matrix. Okay, so those are the matrices A and A dagger. So now if you want to multiply A dagger times A, we can write it using the trick I'm always telling you on how to multiply matrices, yeah? So we would have to write A dagger here, so we need to multiply this times matrix A. So instead of writing it here in the right, as you know, instead of writing matrix A here, we move it above and we write matrix A here. So matrix A has the first column, the second column, all the way up to the mth column of A. Yeah. And we know, because we are going to use our starting point is going to be that this is equal to the identity matrix. Yeah. So we are going to start here and we are going to prove this. Yeah. So we know that the result of this is a matrix that has ones on the diagonal and zeros everywhere else. Yeah. But now look at this. This is beautiful because this means that every element in the diagonal, for example, this element here. So this element here is what? It's the dot product of the corresponding row with the corresponding column. Yeah? So it's C1 conjugate dot C1. And we know that this is equal to 1 because that's the result that we get. But C1 conjugate dot C1, that's the same as the inner product between C1 and C1. And that is equal to 1. Next, look at the second element here in the diagonal. So this element, which is equal to 1 because we know that the result is the identity matrix, but we know by the rules of matrix multiplication that this must be equal to this row dot product with this column, right? Therefore, we know that row C2 conjugate dot product with C2 must be equal to 1. But C2 conjugate dot C2 is equal to the inner product of C2 with itself. So we know that that is equal to 1. And if we work our way through the diagonal up to the mth case, yes, which means that Cm conjugate dot Cm equals 1, which is the inner product between Cm and itself. So we find that all the columns inner product with themselves must be equal to 1. So they are all unit vectors. Yeah. So all Ci's are unit vectors. But that's not all, because we also have all these zeros to check. For example, this 0 here, since this is 0 because this is a identity matrix, every element that is away from the main diagonal is equal to 0. But this element here is equal to, for example, C2 conjugate dot product C1, right? By the rules of matrix multiplication. So we know that C2 conjugate dot product C1 must be equal to 0. But we know that C2 conjugate dot C1 is the inner product between C2 and C1, the Hermitian inner product. And indeed, every single zero that is away from the diagonal is telling us that Ci conjugate dot Cj is equal to 0 if I is different to j, right? Because in every element outside of the diagonal, we are doing one column dot product with a different column, yeah, because we are away from the diagonal of the unitary matrix. Therefore, we are saying that the inner product between Ci and Cj is equal to 0 if I is different to j, which was the definition of orthogonality. Yeah? So on one side, we know they are unit vectors, and then on the other side, we know that they are orthogonal. Therefore, if we combine those two things, we know that the columns of the matrix A must be an orthonormal set. And that finalizes the proof. We proved this direction, but it's very easy to go back, because if we start with the known inner products being 0 if I is different to j and being 1 when the inner product is with itself, we can then figure out that the product of these two matrices must be equal to the identity matrix. So we can go the other way around. Yeah? So we can prove both directions of this arrow. Okay, so that finalizes our two proofs. You see, it's a very elegant proof, and the result is very powerful. And it says things that seem very strange at first glance. So if a matrix conserves the lengths of the vectors, then A dagger times A equals the identity matrix, and then all the columns are an orthonormal set. And we saw the example of the rotation matrix. Rotating doesn't change the length of vectors, and indeed we can check that A dagger dot A equals I, and that the columns of A are orthonormal. And remember, this is a if and only if relationship, so it goes both ways, which means that if you ever find a matrix whose columns are orthonormal, then you know that this matrix is unitary. Yeah? And therefore you know that A dagger dot A is the identity matrix. So these three things are completely equivalent. Thank you very much for listening.